Hello everyone, I'm Paul and today we're solving problem 3479, fruits into baskets free. This is medium and there are at least 2 ways to solve this one, and here I will show you both. If you haven't seen part 2, I recommend you to go and watch that video first, it's in my channel. We're given 2 integer arrays, fruits and baskets. Fruits has the quantity for different types of fruits and baskets has the capacity of different baskets. So let's say we're given this. We need to put these fruits into these baskets, and the way to do this is according to these rules. Each basket can hold only one type of fruit. Each fruit type must be placed in the leftmost available basket with a capacity greater than or equal to the quantity of that fruit type. And if we can place a fruit type in any basket, it remains unplaced. And finally, we need to return the number of fruit types that we can't place in the baskets. So for example, here we have 4 fruits of the same type and we need to place these in some basket here. So we check from left to right where can we place this, and we can't place this here because 3 is smaller than 4, but we can place this here. So now we have already seen this basket and we have used these fruits. Next we are here and we can put these 2 fruits in the leftmost available basket, meaning here. So now this basket is not available and we have used these fruits. Finally, we are here and we are checking if we can put these fruits here. We can't because 4 is more than 5. So we return 1 because there's 1 fruit type that we can't place in any basket. The main challenge for this problem is down here in the constraints. We know that n is smaller or equal to 10 to the power of 5. And this means we can't think in terms of n times n, because this is a very big number. We need to think about something more efficient. And in this first approach, I will show you how to solve this in n times square root n. So this is how this works. We are storing baskets in groups. So this is one group, this is another group, and this is another group. So groups have the same length, and the length is given by square root n. And why are we using groups of this length? Well, because of this. This is how we can solve this in n times square root n time complexity. So we will have an array of groups in which we are storing the maximum value in each group. So first here the maximum value is 5. Next here the maximum value is 9. Finally here the maximum value is 3. So now we are iterating fruits and we are checking in which group can we fit each of these. And we'll have a result which is initially 0. And first we are here and we are checking if 4 is smaller or equal to the first group, and it is. 4 is smaller than 5. So now we know this, we can iterate the corresponding group, meaning this one, and we are checking if we can fit these fruits into some basket here. Remember, we always go from left to right, so first we are checking this basket and it's smaller than fruits, so we continue. Next we are here and 5 is greater than 4, so we can store these fruits here. And now that we are using this basket, we will replace this with 0. And now the maximum value in this group is 3, so this is now 3. Next we are here and we are checking groups from left to right, and first we check if 2 is smaller or equal to 3, and it is. So we go to the corresponding group, meaning here, and we iterate baskets from left to right, and 2 is smaller than 3, so we are using this basket. So this is now 0 and the maximum value here is 0. Now we are here, so we iterate groups from left to right, and first 0 is more than 5, so we continue, and 9 is greater than 5, so we go into the corresponding group, and now we are iterating this from left to right, and first 4 is more than 5, so we continue here, and 9 is greater than 5, so we are using this basket. So this is now 0 and the maximum value here is 4, so we replace this with 4. Now we are here and we are iterating groups from left to right to see where can we fit these 7 fruits. And this is more than 7, this is more than 7, and this is more than 7. And given that we can't fit these fruits in any group, we add 1 to the result. Finally, we are here and we can't fit these fruits here, here, or here, so we need to add another value to the result. This is now 2. And given that we have already seen every fruit type, we can return the result, which is 2. And what this means is we can't fit these 2 fruit types in any available and valid basket. As I said before, time complexity here will be big O of n times square root n, and space complexity will be big O of square root n. So now let's go with the code and hopefully you will get the idea. First we say n is the length of baskets, and now we are building our groups array. So first the size for every group, we'll call this group, is the square root of n, and we are transforming this into an integer like this. And now groups count, meaning the number of groups we have, is n divided by group. And given that we can have, for example, 5 elements, we want to include the last element into some group. So here we need to say n plus group and divide all of these by group. So now we have our groups count, and we can say the array, we'll call these groups, is an array with 0 times groups count. And now we need to fill groups with the maximum value for each group. So for I in range n, groups I divided by group equals to the maximum among this and baskets I. So this is exactly the same we saw a few seconds ago. Now we have the maximum value for each group. Now we can iterate fruits. So result is initially 0, and for every fruit in fruits, we'll have a boolean here, we'll call this used. This is initially false, and this will tell us if we have already used the current fruit type or not. Of course, this is initially false. And now we are iterating every group. So for I in range groups count, first we can say if groups I is smaller than fruit, we just continue, meaning we can't put the current fruit type into this group. And now we can say the value for groups I is 0, position, meaning the position for the current group in the array baskets, in the original array. This is I times group. And now we can say for J in range from the current position to the current position plus 1 group. And it might be the case that this is out of bounds. So here we need to take the minimum among n, sorry, this is n, and position plus group. And in here we can say if baskets J is greater or equal to the current fruit type and not used. Remember, used is up here. This was initially false. So if we reach here and we have not used the current fruit type yet, we can say baskets J is 0 and used is true. And every time we want to update the maximum value for the current group. So we say groups I is the maximum among groups I and baskets. Sorry, this is baskets shape. And if we reach here, this means that we found a basket for the current fruit type, so we can break this loop, meaning we are not checking for any other groups. And here we can say if not used, we add 1 to the result, because remember, we need to return the number of fruit types that we can't use. Finally, we return result. So this is it for the code. Now let's submit this and see if it works. As you can see, this works. It's quite intuitive, but it's not very efficient. So next I will show you the efficient solution. For the second approach, we can use something that's not very beginner friendly. It's called segment tree. So now I will show you how this works. Down here we have baskets, and we are building a tree, a binary tree, to store the maximum value in baskets. And we are building this tree from leaves to the root. So we'll have every value in baskets as a leaf. So this is a leaf, this is a leaf, this is a leaf, this is a leaf. And we are building this binary tree like this. We take the maximum among these two, and it's 5. And the maximum among these two is 9. And we repeat the same in this level. So we take the maximum among 5 and 9, which is 9. And we'll say this is node 1, this is node 2, this is 3, this is 4, 5, 6, 7. So now we are iterating fruits from left to right. So first we have a 4. And we are checking in this tree from the root if we have any available and valid basket. So first, 4 is more than 9, so we can go left. And why are we going left first? Well, because the problem statement says that we need to find the leftmost available basket. That's why we first go left. So now we are here, and 5 is still greater than 4, so we go left again. So now we are here, and 3 is smaller than 4, meaning we can't put these fruits in this basket. So we need to backtrack here and explore the right branch. And 5 is greater than 4, so we can put these fruits here. And whenever we reach a leaf and the value is greater or equal to the current fruit, this means we found a valid and available basket. And here we can replace this 5 with a -1, meaning this is no longer available. And here we return 5. The result is initially 0, and whenever we return something that's not -1, for example 5, the result stays as it is, in this case 0. Because returning 5 means that we found a basket for the current fruit, so the result stays at 0. And now we need to update the tree with this new value. So the maximum among 3 and -1 is 3. And the maximum among 3 and 9 is still 9. So now we are here and we do exactly the same. We start from the root and we are checking if 9 is greater than 2, and it is, so we move left. Now we are checking if 3 is greater than 2, and it is, so we move left again. And now we are checking if 3 is greater than 2 again, and it is, so we can use this basket. So this is now -1. The maximum among -1 and -1 is -1, so this is now -1. And the maximum among -1 and 9 is still 9. Now we are here and we do the same. We start from here, and 5 is smaller than 9, so we go left. Now we have a -1, and 5 is greater than -1, so we need to backtrack. We are here again and we explore the right branch. And we have another 9. 9 is greater than 5, so we move left. Now we are here and 4 is smaller than 5, so we need to backtrack again. We are here, we explore the right branch, now we are here, and 9 is greater than 5. And given that this is a leaf, we can use this basket. So this is now -1, and we need to update this tree. So the maximum among 4 and -1 is 4, so this is now 4. And the maximum among 4 and -1 again is 4, so this is now 4. And remember, here we return 7, and whenever we return something that's not -1, the result stays at 0, meaning we found a basket for this fruit type. Finally, we are here, and 7 is greater than 4. This means we can't go left and we can't go right. We need to return -1 right away. And whenever we return -1, we need to add 1 to the result. So this is now 1. Now we've seen every fruit type, so we can return the result, which is 1. So this is it for the approach. Time complexity will be big O of n times log n. This n is for the fruits array we need to iterate, and this log n is for every search we need to do here. And space complexity will be roughly big O of n. So now let's go with the code, and hopefully you will get the idea. First we say b is length of baskets, and the size for segment trees is usually 4 times b, maybe less, but with this we make sure we have enough nodes for what we need. And the segment tree will be an array with 0 times size, and we can create our build function. This takes a node, left and right pointers, and this is usually a standard template. If we are in a leaf, meaning if L equals right, segment tree at the current node equals baskets I. Sorry, this is L. And we return. Else, meaning if we are not in a leaf, we need to split the array in 2. So we take a mid pointer, and this is right plus left divided by 2, and we call build on each of these sides. So for the left side we'll say build node times 2 from left to mid, and for the right part we call build with node times 2 plus 1. Remember, this is the index, we start from 1, and node plus 2 means we are moving to the child in the left, and node times 2 plus 1 means we are moving to the child in the right. And this goes from mid plus 1 to right. And finally we need to update the tree, so segment tree at the current node is the maximum among the children for this node. So segment at node times 2 and segment at node times 2 plus 1. So now we can call build with node 1 first, and this goes from 0 to b minus 1. Now we have our binary tree, and we can create our function find, and we will use this to find if we have available and valid baskets. So this will take node, left, right, and a fruit. And first we have a failure base case. We'll say if fruit is greater than segment tree at the current node, we just return -1. And just to be clear, this is failure base case. And now we have a success base case, and this is if this is not true and we are in a leaf, meaning if L equals right, segment 3 at the current node equals -1, and we just return the left pointer. And just to be clear, this is success base case. Now we can say the midpoint is right plus left. Sorry, this is mid divided by 2. And first we want to go left. We will call this candidate. And first we call find with the left part, meaning node times 2 from left to mid with the current fruit. And just to be clear, this is first we go left. And if candidate is -1, meaning we didn't find any available and valid basket on the left side, we need to go right. So candidate equals find with node times 2 plus 1 from mid plus 1 to right and with the current fruit. So if no candidate, go right. So now we can update the tree. Segment at node is the maximum among segment at node times 2 and node sorry, this is segment node times 2 plus 1. So this is exactly the same we did before when we were building the tree. And finally we return the candidate. So with this function, now we can iterate fruits. The result is initially 0, and for every fruit in fruits, if we don't find the current fruit, meaning if find from node 1, left is 0, right is b -1, and we are carrying the current fruit. So if this is -1, we add 1 to the result. So this will go on, and finally we return the result. So this is it for the code. Now let's submit this and see if it works. As you can see, this works and it's very efficient. It's harder to understand in my opinion, but it's very efficient. So if you found this useful, please drop a like, subscribe, and see you in the next one. Bye bye.